I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of July 2024. This question is from the section Analysis and it is related to the uniform continuity and the uniform convergence of sequence of functions. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704065. Right. The given question is, let f be a function from the semi-closed interval 0 to 1 closed at 0 end to the semi-closed interval 1 to infinity closed at one end be defined by f of x is equal to 1 by 1 minus x. For n greater than or equal to 1, let Pn of x is a polynomial of degree n, that is 1 plus x plus so on and so forth plus x to the power of n. Then which of the following statements are true? We are given four options. Option 1, fx is not uniformly continuous on the semi-closed interval 0 to 1. Option 2, the sequence Pnx converges to f of x pointwise on the semi-closed interval 0 to 1. Option 3, the sequence Pnx converges to f of x uniformly on the semi-closed interval 0 to 1. Option 4, the sequence Pnx converges to f of x uniformly on the closed and bounded interval 0, c for every 0 less than c less than 1. Let's now discuss the solution of the problem in detail. We are given a function f from the semi-closed interval 0 to 1 to the semi-closed interval 1 to infinity defined by f of x is equal to 1 by 1 minus x. We are given for n belongs to n, the set of natural numbers, Pnx, p suffix n of x is equal to 1 plus x plus so on and so forth plus x to the power of n. That is a polynomial of degree n. Let's call on option 1. f of x is not uniformly continuous on the semi-closed interval 0 to 1. Is it true? That is the question. We have this function from this semi-closed interval 0 to 1 to 1 to infinity defined by f of x is equal to 1 by 1 minus x. That is, f of the domain, that is the semi-closed interval 0 to 1 is equal to the semi-closed interval 1 to infinity, that is the range of f. Right. So we want to prove that it is not uniformly continuous, f of x. We assume the contrary, that is, we assume that f is uniformly continuous on the semi-closed interval 0 to 1 and we look for a contradiction. Agreed. Now we recall this theorem. This theorem states a uniformly continuous function maps a bounded interval to a bounded interval. Right. So we have assumed that f is uniformly continuous on the semi-closed interval 0 to 1. Therefore, f should map 0 to 1 to 1 to infinity. Since 0 to 1 is bounded, 1 to infinity must also be bounded, because by assumption it is uniformly continuous, therefore it maps a bounded interval to bounded interval. Since semi-closed interval 0 to 1 is bounded, and as we have assumed f is uniformly continuous on the interval, by the above result, f of the domain, the semi-closed interval 0 to 1, that is the semi-closed interval 1 to infinity, must be bounded. But this is not true. It is an unbounded interval. So this is a contradiction to the fact that this interval, semi-closed interval 1 to infinity, is unbounded. This contradiction tells us our assumption is false. Therefore, f is not uniformly continuous on the interval. Thus, f of x is not uniformly continuous on the interval, semi-closed interval 0 to 1. So the option 1 is true. So thus we have established the statement given in option 1. We continue in the next slide. Right, that's what we have. We call option 2, the sequence P and X converges to f of x pointwise on the semi-closed interval 0 to 1. So we have to talk about the pointwise convergence of the sequence of functions P and X. Right. We have the function from the semi-closed interval 0 to 1 to the semi-closed interval 1 to infinity, defined by f of x is equal to 1 by 1 minus x. And P and X is a polynomial of degree n. And this can be written as 1 minus x to the power of n plus 1 divided by 1 minus x. Yeah, it's well known. It's well known. If you divide, you get this one. Agreed. Now we want to talk about the pointwise convergence. Therefore, for all x belongs to the interval, limit n tends to infinity of P and X. We are talking about for all x belongs to the interval, semi-closed interval 0 to 1. Limit n tends to infinity of P and X is limit n tends to infinity of 1 minus x to the power of n plus 1 by 1 minus x. Separate them. And it is 1 by 1 minus x because it is free from n, minus x to the power, limit n tends to infinity of x to the power of n plus 1 by 1 minus x. But what is x? X belongs to the semi-closed interval 0 to 1. And what happens to x to the power of n? X to the power of n tends to 0 as n tends to infinity. For all x belongs to the semi-closed interval 0 to 1. So it is 1 by 1 minus x because limit n tends to infinity of x to the power of n plus 1 is 0 for all x belongs to the semi-closed interval 0 to 1. Thus, this is true for all x belongs to this. So, P and X converges to 1 by 1 minus x. True for all x. Therefore, the convergence is pointwise. The sequence P and X converges to f of x. 1 by 1 minus x is f of x. Pointwise on the semi-closed interval 0 to 1. So, we are establishing the statement given in option 2. Therefore, option 2 is true. So far, first option and second option are true. We move on to the next option, option 3. The sequence P and X converges to f of x uniformly on the semi-closed interval 0 to 1. We have already proved it is pointwise convergence. Now, now is the convergence uniform? That's what we are asking. So we have already seen that the sequence Pnx converges to f of x, that is 1 by 1 minus x, pointwise on 0 to 1. We are now asking whether this convergence is uniform or not. So note that for every n belongs to n, this Pnx is a polynomial and it is bounded on the semi-closed interval 0 to 1. Yes, yes. For every n belongs to n, Pnx, that is the polynomial, is bounded on the semi-closed interval 0 to 1. So now assume that the sequence Pnx converges to f of x uniformly on 0 to 1. That means we are trying to get you a proof by contradiction. So assume that it converges uniformly and try to get a contradiction, then the convergence is not uniform. But in option 3, it is given that it converges uniformly on this. So assume that the sequence converges to f of x, 1 by 1 minus x, uniformly on 0 to 1. If you assume like this, right? Now we recall another theorem. If fn, the function from a to r, that means a real valued function defined on a, is bounded, if this fn is bounded on a, for every n belongs to n, then fn converges to f uniformly on a. This is it. Fn, a to r is bounded. That means it's a sequence of bounded functions on a. And if fn converges to f uniformly on a, then the outcome is the limiting function f is from a to r is also bounded on a. So this is the result. So now by this result, and you know this Pnx are bounded here, and by assumption fn converges to f on a, that is your assumption. Therefore the limiting function f of x, that is 1 by 1 minus x, must be bounded on a. A means the semi-closed interval 0 to 1. But this is a contradiction. Why? Why it is contradiction? Because f of x is equal to 1 by 1 minus x is unbounded when x is approaching to 1. When x is approaching to 1, it is unbounded. So therefore, it's unbounded on 0 to 1. And you are getting a contradiction. You are getting a contradiction. So this contradiction tells you the convergence is not uniform. You have assumed that the convergence is uniform. You got a contradiction. The convergence is not uniform. But in option 3, it is given that the convergence is uniform on the semi-closed interval 0 to 1. So therefore, the option 3 is not true. Agreed. We move to the last option in the next slide. Right, option 4. The sequence Pnx converges to f of x uniformly on the closed and bounded interval 0 to c for every 0 less than c less than 1. This time, that semi-closed interval 0 to 1 is removed. In that place, we have a closed and bounded interval 0 to c where 0 less than c less than 1. So we want to support this statement. So we will establish this result. Right. To prove this result, we need a very well-known theorem called Dini's theorem. So there is much of hypothesis. Hypothesis is more in this Dini's theorem. Dini's theorem. Let Fn, n belongs to n, be a sequence of, it's a sequence of continuous real valued functions, each Fn is continuous, on a compact set A. So in the place of A, we have the semi-closed and bounded interval 0 to C, and the closed and bounded intervals on R are compact sets. Agreed. And in the place of Fnx, we have Pnx. Okay, we will verify all those things. And suppose that the sequence Fn converges to a continuous function f pointwise on A. Option 2. The sequence Fn is a monotonically increasing sequence on A. Then the sequence Fn converges to f uniformly on A. That means the pointwise convergence will give you the uniform convergence under these circumstances. The hypothesis is lot of hypotheses there. We will verify the hypothesis one after the other. Try to apply Dini's theorem. Notice that each Pnx, that is 1 plus x plus so on and so forth plus x to the power of n, it's a polynomial. It is a continuous real valued function. Why? We know polynomials are continuous. So Fn, n belongs to n, be a sequence of continuous real valued function, right? And in the place of A, we have 0 to C. It is compact. Closed and bounded interval 0 to C is compact. For every 0 less than C less than 1. Why? Because on R, who are compact sets? Closed and bounded subsets are compact. Agreed. A is compact. Now, the sequence Pnx converges to f of x, that is 1 by 1 minus x, pointwise on the closed and bounded interval 0 to C. We have already seen the semi-closed interval 0 to 1, it is pointwise convergence, and the closed and bounded interval 0 to C, where 0 less than C less than 1 is a part of the semi-closed interval 0 to 1. Therefore, the pointwise convergence is valid even in this because it is a part of 0 to 1. And it converges, and the limiting function, that is f of x, is 1 by 1 minus x, is continuous in the closed and bounded interval 0 to C, 0 less than C less than 1. Yes, yes. Numerator is continuous, denominator is continuous, and one by the other is also continuous, right? Agreed, agreed. F to a continuous function f pointwise on A. So it is pointwise and the limiting function is continuous. So the last condition, f Pn plus 1 x minus Pnx. So write down Pn plus 1 x, polynomial of degree n plus 1, minus Pnx. So if you subtract, you will get x to the power of n plus 1. And in the interval 0 to C, it is greater than or equal to 0 for all n. That means to say this sequence Pnx is monotonically increasing sequence on 0 to C. That is your last condition. Then the Dini's theorem can be applied. And you get, by Dini's theorem, the sequence Pnx converges to f of x uniformly on the closed and bounded interval 0 to C for every 0 less than C less than 1. Thus we establish the truth of option 4. Thus option 4 is true. So combining all the options, we get the answer to this question. Option 1, 2 and 4. That is the detailed discussion of the solution of the given problem from the section analysis, which is related to uniform continuity and uniform convergence of sequence of functions. It is a very good question. And in this, you have used theorems, three theorems in all.
One of them is Dini's theorem. The other two are already there. So that means to say one must be very well aware of the concepts of uniform continuity and the convergence, uniform convergence, and the properties and the results thereof are very, very important. So read the section uniform continuity and uniform convergence, and especially this Dini's theorem, and several other theorems are there. So you make a good notes of it so that they will be handy in your examination. I am sure that you have understood the solution of this problem, and I am also sure that you liked this video, because you have come up to this means you like the video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet once again in another episode of learning. I wish you all the best. Thank you.